Hi guys. Video today. I will do 2 of the lessons in one video. The lesson here just follows on from our auxiliary angle form from last lesson here, and it's just doing everything we did from that last lesson, but then sketching it once we convert it. So pause the video here and just have a go, refresh your mind from last lesson, use your auxiliary angle method and convert it into the form we need. And from there, then we'll go back and revise some of that trig graph information and sketch it. Okay, assuming you've had a go at converting it, hopefully based on last lesson, I won't go through it all again, but thinking about what we did with our formulas, you end up with it in the form of 2 sine theta minus pi on 6. Now we just graph it. So again, this isn't any new content, it's just using from trig graphs and a bit of last lesson. We got a sine graph, amplitude of 2, and we've got a shift pi on 6, and it's going to be to the right. Now, pardon me. We still do it over the original domain, okay? We don't change the domain in these questions, over the original domain. So you can see where I've mapped out the graph in my dotted line. That's where I would use pencil. I've gone over where I am in my domain in red there, okay? So amplitude of 2, shifted at pi on 6 over and in between my domain. All right, give the next one a go. Pause the video. Do your auxiliary angle method and then sketch it. See how you go. And let's see what we got. Hopefully you end up, this one was in degrees, with 5 cos theta minus 53. Again, amplitude of 5. I need to put that on there, don't I? 5, negative 5. And this time it got shifted over again, but 53 degrees. So you can see again how I'm mapping it all out. And, you know, I should write the official degrees, but I'm just mapping out, showing you how I'm getting those again over the original domain. Don't change your domain at all. And that's it. So very short lesson, nothing new there, was just combining 2 different skills. You can definitely have a go at the exercise now on all of that. But I am going to push forward into lesson number 2, which is then going into some of the T-formula. The reason I'm going to push through with this one is because I'm also not going to be at class on Wednesday. So I will do both the lessons in this one. That'll give you time to work through questions and exercises, whether you want to watch both parts of this video now or you can go to that exercise now and come back to this. It's up to you. Otherwise, T-formula. These are our formulas here that we are proving to start with, but then again, just like recently, the proofs, we can use these formulas. We don't have to prove the formula every time we want to use it. However, it's in the syllabus. We do need to know how to do the proof still. So, as with all proofs, I like for you to just pause the video, copy all this down, and that way when I'm talking through, you know, all the different parts, you can follow along. So do that. All right, so assuming you've got all this down now, let me talk through this proof. So the T formula is actually a handy formula. You'll notice at the top of my screen in the box, we've got that if T is equal to half theta or theta on 2, I can then use these 3 formulas. But notice how down the bottom, if we have a simple substitution, being T just equal to tan theta, we can then just alter these formulas and use them as sine of 2 theta, cos theta, and tan of 2 theta. So handy little trick there to know about your T formulas. But let's prove these ones in the top first. So first thing I'm going to say is, well, I'm going to start with, okay, tan theta. I know tan theta I could manipulate to be tan of 2 theta on 2. if I do that, I then can sub that into my double angle formula, which I've just provided over here. That should be familiar to you. It was at the very beginning of this booklet, going back over year 11 identities. And I sub all of that into my double angle formula. And what do you know? If T is what we say it is, then that's what the definition up here says, half theta. I can then end up just substituting in T for tan of theta on 2, and I end up with this formula, which is the very first T formula for tan. From there, to get my other two formulas, I'm just going to do Pythagoras. You can see my triangle over here. Put theta in. I know that tan is opposite over adjacent, so it's got to be 2t over 1 minus t squared. And then everything else over here is just Pythagoras. Okay. Once I've done Pythagoras, then I can write an equation, which is exactly what I do down here in these highlighted formulas, for what sine of theta would be or cos of theta would be. And there we have it. Now, one important thing with all of the questions when we solve them via the T formula, remember that the tan graph has asymptotes, okay? So when we're letting T equal tan theta on 2, we can't specify whether that has a solution, I should say, for where the asymptotes would normally be. Okay, so there's part of here we can't test for, right? Because that's where asymptotes are. So that's what this last part down here just is talking about. Don't forget tan has asymptotes, and where those asymptotes are in both degrees and radians. All right, so pi on 2 or 90 degrees and so on. So you'll see when we go through these next few pages of questions, we always want to test, okay? Testing for those values to see if they are a solution or not. So let's have a look. Turning over. Nice, straightforward T formula substitution questions here. We've got, okay, it's telling me that tan is theta on 2, which tells me straight away I'm using this top box, these formulas here. So I'm just substituting sine theta plus cos theta, replace it. Sine theta is 2t on 1 minus t squared. Cos theta is this one. Plus them together, do some algebraic work. The next one, same thing, just some more algebraic work. It was a bit ugly, but it cleaned up pretty nice. So replacing the cos theta and the sine theta with my formulas, clean up the algebra, I end up with fraction on fraction, simplify, flip and times, and I end up with t. So I'm going to keep moving forward, but again, do that substitution and everything yourself and practice that algebraic skill. Next one, getting a little bit harder. We've got some identities thrown in here, but again, cosec theta, I know that's 1 over sine theta. Cot theta, it's 1 over tan theta. And again, I need to show that's equal to cot theta on 2. So what do? I make the substitution for what 1 over sine theta is just going to be the inverse of this formula up here, which is why it's just flipped upside down, plus it together. I end up with 1 on t. Remember, t is equal to tan of theta on 2. And when I sub that in, I know that 1 over tan is cot, which is the right-hand side. If you want to pause the video and give B a go on your own, it's just straight substitution and show that it equals tan theta on 2. That's my solution there. Again, not hard, it's just being careful with the algebra. So I won't go through it because you can see exactly what I'm doing, just substituting in those values. This is now where we're going to start. Okay, we've practiced, using the T formula. We're going to look at solving some trig equations now using the T formula. So this is where it can be really useful. Now, this box up the top is just going back over what I said earlier about the asymptotes, checking for solutions at those points. Sorry. Okay, Let's just have a look though at how we can go about a question like this. It says use a t substitution to solve. Tan theta on 2, sine theta equals 1. So I say, well, I know tan can be tan theta on 2. So now I'm just going to replace t for tan theta on 2, which gives me this becomes t. Sine theta, I replace with the sine formula for my t formulas. Clean it up, and I get t is equal to plus or minus 1. From there, I come back to my substitution. I said, well, that's what tan of theta on 2 is equal to. So then I'm saying, okay, I need to solve. And remember, equations like this, what I'm actually thinking in my head is tan, let's just say alpha equals plus or minus 1. I use my triangles, and I know straight away that that's going to be a related angle of 45 degrees. I come over to my unit circle over here. It's plus and minus. However, I'm not doing all 4 quadrants because remember when we have trig equation, if something is affecting the angle in here, it affects my domain. So, I put it over here. Instead of being between 0 and 360, when I'm dealing with theta on 2, I have to then manipulate that domain. So it's now only between 0 and 180. So that's why I'm only testing in the A and the S quadrants, not all of them, even though it's plus and minus. And you can see my working up here. So that theta on 2 is equal to 45 and 135 from my unit circle. And then times through by 2, I get my answers. Notice then what I need to do over here. Check theta equals 180. So check that solution. All right. So again, I'm looking in the domain that I have here, and I need to test those points where the asymptotes would normally lie. All I need to do to check that is put it back into the original question. Okay, when you substitute 180 degrees into the original question, then if it works, that means that 180 degrees would also be one of my answers. If it doesn't work, then it's not. Now, when I put 180 degrees into the original question, I get tan 180 on 2, sine 180, and that's supposed to equal 1. Straight away, I know that 180 on 2 is 90. Tan of 90 has no solution, so therefore it doesn't work. So that's why then I say, okay, nope, it's not an answer, but I have to check. And if you don't do that check, then you will lose marks. Remember, the domain is your giveaway for whether you're in degrees or radians, okay? So have a go at this next one. Remember, start by just making t substitutions, clean it up, solve for t, then replace it with tan of theta on 2 and solve the trig equation. Otherwise, if you've given it a go, let's go through the solution. Okay, filled into my formulas, cleaned it up. That's all just algebra, algebra, algebra. I end up with t is equal to negative 1 on root 3. Thinking about my triangle, what would give me, tan of something being 1 on root 3? Well, it must be a related angle of pi on 6. Notice here, I'll put it in yellow, I'm adjusting my domain. It was originally over 0 to 2 pi, but when I have an x on 2, something affecting my angle, I then divide through the domain by 2. So now my domain's only over 0 and pi. So I got my related angle. I need to look for where tan is negative and only between 0 and pi. So the only possible answer you can see I've put over here my unit circle would then be pi on 6 in the sine quadrant, which gives me an answer of 5 pi on 6. So therefore, x on 2 is equal to 5 pi on 6 times through by 2, and I get 5 pi on 3. Remember, don't stop there. I need to check, all right? Check for x equals pi. So again, in this domain, I'm going to check where my asymptotes would usually be. So by checking x equals pi, I've just subbed it straight into the original question. And what do you know? It actually does equal -1. Therefore, it is a solution. So notice my final answer over here, I have both 5 pi on 3 and pi as my final answers. Okay, keep going. Go to the next page. See how you go with the next few questions. Same processes. Otherwise, let's jump into it. Last page here we've got, okay, show that the equation can be written as. Usually when they have a show question like this, it's going to help you somehow. And it does sort of, I guess, breaks it up for you a bit. We make our t substitutions, nice and easy, do some algebraic work, and yep, that's pretty straightforward. We can get to t squared equals √3 on √3 times t. Hence means use exactly what you just solved. So we're going to solve that equation. We're going to solve it, all right. When I solve that, I end up with t is equal to 0 or √3. When I then make my substitution that tan of x on 2 is equal to 0 or √3, notice I have to change my domain once again, dividing through by 2 because it's x on 2. Which means that, okay, I need to look for something in my triangle here, opposite over adjacent, giving me an answer of √3, which must be pi on 3. Opposite over adjacent would give me that. So, come to my unit circle. I need to check between 0 and pi. It's a positive √3. So, where is tan positive between 0 and pi? Well, just there, where pi on 3 is. Remember 0, tan of 0 is 0. So, therefore, I've got x on 2 is equal to 0 or pi on 3 times through by my 2, and I get my 2 answers here. What do I have to do again? Check where those asymptotes would normally lie, okay, in my original question. So then I say, all right, well, and if you're not sure why if you're thinking, hang on, but isn't the asymptote at pi on 2? Yes, but we're solving this for x on 2, okay? So then when you solve that equation, that's why I'm testing for pi. But yes, you might be thinking, why am I testing pi when pi on 2 is normally where that first asymptote is? But that's why, because of that angle change. Okay, so I throw x equals pi back into the original question, and nope, it doesn't work. Okay, sine of pi gives me 0. Cos of pi, oh wait, is -1. It is a solution. There we go, good pickup. Cos of pi is -1, so then it's left-hand side -1, right-hand side, so it is a solution. Which then means I just put pi over here as well. There we go. And last one. Don't be afraid if they have the double angle version. We know that, come back up to that original page here. If it's the double angle, then we just go off these formulas and this t substitution. So that's all we're doing on this very last one here. Instead of tan being theta on 2, we just have tan is equal to theta. Then same thing goes through. Sub in my formulas, clean it up, and the same process over again. I check again this time. Notice this time nothing was affecting my angle, so I didn't have to change the domain, which was nice, which also meant that I was actually testing my actual asymptotes this time within that domain. Okay, so pi on 2 or 90 degrees and 3 pi on 2. That's why I'm testing the actual asymptotes. And I just got lazy, but you should always show that substitution line where you're subbing 90 degrees back into the original formula. But I can tell you they both work, so make sure they're both in both answers there. Okay, so there we go. That's how we can solve trig equations using the T formula. Now, a lot of those questions you can check. You can do your auxiliary method formula and you'll get the same answers. From here, I'm just going to be breaking up all the different types of trig equations, and that's the remainder of the booklet. We look again at some further ones of them, but yeah, that's basically most of the topic down packed now. Okay, it's just solving trig equations, and the two main new formulas are your auxiliary method and your T formula. So work through those exercises, and next week we'll finish off the topic on Monday with just going through the remainder of the trig equations.